Hello, AP Chemistry students. So today we are going to review Unit 3 from the College Board for the AP Chemistry curriculum. So Unit 3 starts off with intermolecular forces, and then it goes into solids, liquids, and gases, solubility, and then there's even some stuff like photoelectric spectroscopy, Beer's law, things like that. In this video, we're just going to start with the intermolecular forces. I think this is one of the hardest topics to grasp. I also think that it's one of the trickiest topics, and I think the College Board likes it, all right, because not only is it so important in everyday life, it explains kind of the properties of all materials around us, but it's also a spot where kids often get it wrong. And I think the College Board likes having those trickier questions to kind of separate the threes from the fours from the fives. So we want to really review Unit 3. We want to be really good at it. We don't want to make some common mistakes that potentially a lot of other kids are going to be making. So this whole video will be looking just at our intermolecular forces. There will be more follow-up. All right, so just intermolecular forces to start with. All right, just a couple of things that are going to come up. This is review, so we've already seen this, but electronegativity differences, right? We know that if there is a small electronegativity difference between two atoms, that's going to be more of a nonpolar covalent bond. If it's a bigger difference, about 0.5 and above, that's going to be a polar covalent bond. And then a really big difference, right? Specifically metal and nonmetal, that's going to be ionic. Molecule shapes, it'll come up just a little bit as far as their symmetry. All right, electron clouds, we're thinking about those orbitals where the electrons are. You have inner shell electrons. Those aren't going to matter as much for us, but they're important. Pi bonding, right? How most of our covalent bonds will be sigma, but pi bonding will sometimes show up. And Coulomb's law. Coulomb's law is probably the most important piece of all of this intermolecular force, because intermolecular forces is really attractive forces, and that's from Coulomb's law. So these intermolecular forces, they're going to explain the physical properties of a material, right? That's why it's so important for us, because any material we look at, if we go down to its atomic level structure, its molecular structure, the IMFs happening there will explain the properties we see at our macroscopic scale. So some of the properties we'll see a little bit in this video, and then we will see in later videos. The state of matter at room temperature, the boiling point, the evaporation, the condensing, the melting point, the freezing point, right? So a lot of phase change stuff, and then solubility, all right? So anything having to do with the phase change, IMFs are part of that story, and the solubility of molecules, anything happening in a solution, IMFs are part of that story. So that's a lot of chemistry. So first thing I want to point out, we just need to keep this model in our heads of what a solid, liquid, and gas look like at that atomic level, at that molecular level, right? So the solids, different types. Here we have an example of a crystalline solid, but our solids are really close together. Our liquids are spread out relative to the solid, but still very close. And our gases are whizzing around, all right? And we see on the bottom, increasing IMFs. So we know solids have more attraction, gases have less. Right up top, we see increasing kinetic energy. That'll be more important in a later video. So I thought this was just a great picture. So something that's going on in the world today, right? We do not want to be the liquids. We do not want to be the solids. We want to be the gases, right? That's where we got those cool shades on, right? But think of it as like the social distancing of molecules, right? Intermolecular forces, their state of matter. So Coulomb's law. London dispersion forces, they are going to be a result of the Coulombic interactions between temporary fluctuating dipoles, all right? London dispersion forces are often the strongest net intermolecular forces between large molecules. So Coulombic interactions, right? We want to remember Coulomb's law, right? The force of attraction, it's equal to, K is just a constant, we can disregard that, Q1 times Q2. Charge of the nucleus, right? Protons in the nucleus, positive charge, times the charge of the electron, divide it by the distance squared, all right? If the force is less than 0, it's an attraction, which is why the proton times the electron gives us that negative, which is attraction. If it's 2 protons or 2 electrons, right, positive, positive, or negative, negative, that force is going to be a repulsion, right? We care about the attractions, though. So when we're thinking of Coulomb's law, we're thinking about what's going on in the nucleus, right? Typically how many protons and how far away an individual electron may be, right? Which is why the electron cloud is important, because the further the electrons get away from the nucleus, because it's r squared, the further away, that has a pretty big impact. And those inner shell electrons will kind of block, right? Because they'll cause their own repulsions. They will block outer shell electrons. So the London dispersion forces, right? They're named after scientist London. These dispersion forces, they are fluctuating dipoles. They are not permanent dipoles, all right? They are fluctuating, and all molecules display London dispersion forces. All molecules have some fluctuation in their electron cloud, all right? So when we talk about the fluctuating, typically the electrons are evenly spread throughout an atom or throughout a molecule, all right? But occasionally we get asymmetrical distributions, all right? It's temporary, all right? So what ends up happening is we get more of the electrons on one side of the atom, more of the electrons on the other. When we get that fluctuation, right, when there's more electrons on one side, we start to get a Coulombic interaction, right? We get a partial negative and a partial positive. It is temporary, and then it goes away, all right? So the electron cloud, it changes over time. It's typically staying symmetrical, but it is having these fluctuations. All right, now, it is often going to be the strongest interaction in large molecules, all right? As we get larger molecules, they're gonna have more electrons, all right? And more electrons is gonna be an important answer to a lot of AP questions, all right? More electrons is gonna allow for there to be more London dispersion forces, right? More electrons is gonna allow for more fluctuations. So the dispersion forces, they increase with increasing contact area between molecules, right? That's gonna be an important piece. So if we're looking at 2 molecules, these are isomers of each other, right? Pentane and neopentane, C5, H12, all right? If it's in a straight line, it's gonna have more surface area. As we get like these branched organic molecules, they're actually gonna reduce their surface area. So the dispersion forces are actually stronger when we have more surface area, all right? So dispersions are gonna be more important when we have these like straight long molecules, all right? And it's gonna increase with increasing polarizability of the molecules, all right? So in a neutral molecule, right, we have our nucleus in the middle, and then our electrons around it are moving about, all right? And they can be polarized, right? If we introduce an ion or a dipole, if we introduce something towards it, we can get the negative charge to line up on one side, and the other side will become slightly positive, all right? A better example of that, we have a neutral species. You bring a positive ion near it, all the electrons are going to flock to that side, right? So the molecule has now been polarized temporarily by that induced ion, right? Even if we put a dipole near it, that can still have the same effect. So the polarizability of a molecule is how well it's able to interact when something like an ion or a permanent dipole comes near. And just again, that polarizability, we're saying how well molecules can polarize. Larger molecules, typically more polarizable. They have more electrons. More electrons means they can be spread out into different combinations, creating different slightly positive sides and slightly negative sides, all right? Typically as well, when we get a bigger atom, all right, when we have electrons that are in higher energy levels, they are further away from the nucleus, they're held less tightly, they can move much easier. So bigger atoms, those electrons, those outer shell electrons, they're going to be more polarizable as well, all right? Now, the polarizability of a molecule increases with an increasing number of electrons in the molecule and the size of the electron cloud. It is enhanced by the presence of pi bonding, right? So first off, as we get more electrons in the outer shell, that's more stuff that can move around. That's going to make greater partial charges. So having these lone pairs on the elements further to the right, those are more electrons that can be moved around. And then as we go further down on the periodic table, right, we're only looking at the outer shell electrons, right? The outer shell electrons, they're spread out over a larger area. So when we have that larger area, we can get some electrons on one side, we can get these pretty dramatic partial charges. So both of those are going to be important in understanding the polarizability of a molecule. If it has more electrons in its cloud, and if that cloud is bigger, more area for it to be spread out over. All right. Now, keep in mind, the outer electrons are what we care about. We're not thinking about any of the inner shell electrons, and those inner shell electrons, they are repelling the outer shell, making the outer shell electrons easier to move around, which means more polarizable. All right, and again, size matters. All right, if we spread out the electrons over a greater size, we can get more types of distributions. All right, and then it mentions pi bonding. All right, pi bonding is important because when we have a covalent bond and we have a sigma bond, it's kind of, the electrons are kind of confined to a pretty small space in the sigma bond. Now, not to say that these electrons can't be polarizable, but they're already kind of confined to a small space the way those orbitals overlap. In the pi bonding, it's the p orbitals, unoccupied p orbitals overlapping, and that has much more space. So it's much easier to polarize a pi bond. So if we see pi bonding, that can lead to a molecule being more polarizable, which will be important. Now, the term London dispersion forces should not be used synonymously with the term van der Waals forces. All right, van der Waals forces, it's kind of describing any molecular attraction. So the dipole-dipole, the dipole-induced dipole, the instantaneous dipole, which is like a London dispersion force, all of these things fall under the category of van der Waals forces, which is why the College Board does not like using the term van der Waals forces. So please never use that. An iconic image in all textbooks, they always have the gecko, right? The gecko, it can stick to the walls because there's a lot of attraction because of all of the folds and all of the small like hairs in the gecko's skin, right? It has a lot of these, it'll say van der Waals forces, but that's not a term we are going to use. I don't think we really used it much in class to begin with, all right? But do not use that term. Mr. College Board does not like it. All right, so now the dipole moment of a polar molecule leads to additional interactions with other chemical species. All right, we're going to do a lot of review in the next couple of slides. So I just want to draw your attention. Polar and non-polar molecules, that's what we're looking at. A polar molecule with a non-polar molecule, what's the difference? All right, first off, we need to remember our electronegativities. Knowing these 5 is really important, right? Fluorine 4.0, oxygen 3.5, nitrogen 3.0, carbon 2.5, hydrogen 2.1. All right, we need a big difference to have a polar molecule. We get a non-polar molecule when it's a really small difference, right? So carbon and hydrogen together, that is always a non-polar bond, right? That difference of 0.4. So it's knowing the electronegativities, it helps explain how the electrons are shared, right, when there's that orbital overlap. So in this top example, we have Cl with a Cl, both 3.0. All right, now this is a diatomic molecule, a Cl2, but it's a non-polar bond. No side of the molecule is pulling the electrons towards it. It's like a very even tug of war, whereas HCl, H being a 2.1 electronegativity, Cl being 3.0, we get the polar bond, right? The partial charges, the hydrogen, because its electron shell is being pulled away from it, becomes slightly positive. Now, slight, not an ion, but a permanent slightly positive, and the chlorine is slightly negative. All right, that will endure. And then all of our diatomic molecules, again, because they have the same electronegativity value, they'll always be nonpolar. Often anything CH, anything organic, carbon and hydrogen nonpolar, And something like carbon dioxide, carbon and oxygen do have a pretty big difference in electronegativity. So we see the slight charges, but it is a symmetrical molecule, right? That linear shape. And the permanent dipoles will actually cancel each other out. So we will get non-polar molecules that do have polar bonds, right? And again, that's anything that's symmetrical. And I remember I said symmetrical has no lone pairs around that central point, right? So that carbon has no lone pairs. That's something to keep in mind. Now, our polar molecules, right, they have some net pull in any one direction. So HCl, the NH3, they're all pulling inward. We get this resultant vector up. The CH3Cl, right? So we'll definitely see review of bonding, and this will come up again, but just remember a polar molecule, right, has this pull to one side of the molecule. And if it's symmetrical, like BF3 or CCl4 down here, if it is a Vesper shape with no lone pairs and it's all the same species, they're gonna cancel each other out. All right, now again, the definition of a polar molecule is something that lines up in an electric field. All right, so something like carbon dioxide would not line up in this electric field. Anything with non-polar bonds would not line up in this electric field, right? If we put the electric field, all of the slight negative sides will be attracted to the positive side of the electric field. All right, so one more thing to keep in mind, when we represent a polar molecule, right, there's two ways we can do it. We could do the bond dipole arrows, right? We typically like to show the movement of the electrons. So the arrow points towards the more electronegative atom, all right? And we put that little bar. So the electrons are moving from carbon towards oxygen, right? Oxygen's pulling stronger. The electrons are moving from hydrogen towards oxygen. And we can write the partial charges, right? It is that Greek symbol, that squiggly S. So any element where its electrons are being pulled away from it, it now has more positive charge from its nucleus relative to the electrons around it. So that's why they become partially positive. And the oxygen, that central atom, becomes partially negative. It is pulling more electrons towards it. So there are more electrons near it than the number of protons it has in its nucleus. All right. So that's all background to understand what we're looking at right now. We are calling the dipole-induced dipole interaction. All right. So we have our non-polar molecule, right? The O2 molecule, the isolated O2 molecule. By itself, it's non-polar. Neither side has any pull. It does not have any partial charges. But you put something polar near it, something with a permanent dipole. Here our example is a water molecule, all right? And it's going to induce a dipole in the oxygen molecule, right? So the fact that the water is near the oxygen, that slightly negative charge when it comes close to the oxygen molecule, it pushes the electrons away from this oxygen atom right here, right? And so the electrons get pushed to the other side of the molecule. And since they're on this side of the molecule, this side becomes slightly negative, all right? And the initial side where the electrons were pushed away from by the permanent dipole becomes slightly positive, all right? The opposite interaction can occur too. If the hydrogen side of the water molecule is near an oxygen, because the hydrogens are slightly positive, the electrons from the oxygen will rush to that side, all right? So the electrons in a non-polar molecule will move about and will be induced if there is a permanent dipole near it, all right? A permanent partially charged molecule near it. All right, now the magnitude of the dipole of the polar molecule is going to be important, right? If we get a stronger dipole near it, then the non-polar molecule will have more, it'll be induced greater. So HCl, for example, is a pretty strong permanent dipole. So if this comes near any non-polar molecules, it's gonna have a pretty big impact, right? Because of its magnitude. Now, the other factor, right? So these forces are always attractive. The strength of these forces increases with the magnitude of the dipole of the polar molecule and with the polarizability of the nonpolar molecule. All right, we still want to think about the nonpolar molecule. How well can those electrons be moved about? Right, that is its polarizability. So something like S8, this is a bigger molecule with a lot of electrons. It can be induced a bit easier, all right, because it has so many electrons. Whereas our small molecules like helium or H2 or O2, they're going to be less polarizable. They have fewer electrons, and those electrons are held closer to their nucleus. All right, so again, the more electrons we have, the more polarizable, and that's an important feature, the polarizability of the nonpolar molecule when we think about dipole-induced dipole interactions. All right, again, when we're thinking down the periodic table, the bigger the atom itself is, the further away its electrons are, more polarizable. All right, and again, we also talked about the pi bonding. So the C2H2, the ethine molecule, will be the most polarizable of these three. So it can have stronger dipole-induced dipole interactions if it is placed near a polar molecule, right, with that permanent dipole. All right, so that's one type of interaction. Now we're looking at the dipole moments of a polar molecule leads to additional interactions with other chemical species. So the same topic, but we're thinking about dipole-dipole interactions. All right, these are present between polar molecules, so two polar molecules. The interaction strength depends on the magnitudes of the dipoles and their relative orientation. Interactions between polar molecules are typically greater than those between nonpolar molecules of comparable size because their interactions act in addition to the London dispersion forces. So in the previous slides, all right, this was dipole-induced dipole. That means a polar molecule with a nonpolar molecule. Now we're doing dipole-dipole. That is two polar molecules, right? And the way they will line up, the partial positive charge of one molecule will have an attraction, and we're always going to use dashed lines to represent the attractions with the negative partial side of another polar molecule, right? Two ways they can line up, so their orientations will matter, but the important part is that the negative partial charge of one molecule will always be attracted to the positive partial charge of another polar molecule. All right, now something to think about with their orientations. The orientations will start to dictate the shapes they'll start to take on. So when we think about HF molecules, they're going to start to get this kind of up and down chain, all right, because of the space between them and because of how the hydrogen's attracted to the fluorine of a different molecule, and then the fluorine from a different molecule is attracted to another hydrogen. It just keeps going. All right. Now, if we have something like NH3, again, because of its shape, it starts to line up in a straighter line. And it's doing this because it just doesn't have the space for the nitrogen to get near other spots. Now, our water molecules are incredibly important because of their small shape and that bent shape. They're able to form attractions in multiple directions. So that's why they almost form more attractions. All right, and again, the dipole-dipole, it's only stronger than comparable forces like LDF or like dipole-induced dipole. It's only stronger when we're thinking of a comparable size. So ethane and formaldehyde are comparable sizes. Ethane is only carbon-hydrogen bonds, so it's nonpolar, whereas formaldehyde has the carbon-oxygen double bond, pi bonding, and the difference in electronegativity forming that permanent dipole. So formaldehyde molecules will have dipole-dipole attraction, right? Whereas the ethanes will not. So, but you can only compare them because they have a comparable size, right? So that's why we can say formaldehyde has stronger attractions because of dipole-dipole than the ethane. It's because they're a comparable size. Often we don't have a comparable size. So often you don't want to just compare the individual intermolecular forces. All right. Now, ion dipole forces are attractions ion dipole forces of attraction are present between ions and polar molecules. Those tend to be stronger than dipole-dipole forces. So just going back to like all of these types of chemical bonds, nonpolar covalent bonds, the electrons are very evenly spread out, right, among both atoms. Polar covalent, one side is getting its electrons pulled away, the other side has more of the electrons. We're showing the electrons in blue and the positive charge in red. And then in the ionic bond, the metal is actually losing the electron, right? It's forming that ion that is a permanent charge, not a dipole, right? It's not a partial charge. It is a full-on charge, and the chlorine is getting the full-on negative charge, right? So this is like full credit. B over here, the polar covalent, that's like partial credit, and then non-polar over here, that's no credit. All right, and then of course an ironic bond is just a really funny joke, so that's why we have the laughing emoji. So when we think about that, ion dipole forces of attraction, right? That's when an ion is near a polar molecule. That happens all the time when we dissolve a salt, right? Water molecules, they're a universal solvent. They surround the ions, right? The positive ions get surrounded by the negative part of water molecules, which is always the oxygen. And the negative ions get surrounded by the hydrogen side of the water molecules because the hydrogens are slightly positive, right? So we have seen ion dipole forces of attraction several times, and this is a really strong attraction, all right? It's strong because the ion itself has a greater Coulombic magnitude than the partial charge from a polar covalent bond. All right, and the way we would represent that, again, the polar molecule has the partial charges. We use the dashes to represent the attraction, and then we have the negative charge on the ion, right? So in any free response question where we are asked to draw out an attraction, right, here are the ways we could represent the ion with the negative charge. We could represent the polar molecule with the Greek symbol for the partial charges, and we can represent the attraction with the dashed line. All right, and again, the charge of the ion will matter. Something like a magnesium 2+ will be more attractive than perhaps like the sodium 1+, right? They are going to be more attracted to a larger charge, and that is Coulomb's law. All right, now there is ion-ion interaction. That is the lattice, right? The formula unit of the lattice, and that is going to be a really strong attraction. All right, but just keep in mind, salts will dissolve readily in the presence of water. And many reasons for that. We can think about the entropy of that. We can think about the heat of the solution. But again, I just want to show you it's not really an important part. We really want to think about more so the non-polar and polar molecules, but ion-ion interaction, that's going to be really strong as well. All right, so again, it's all coming back to Coulomb's law. So we're always thinking, even like if we're thinking of the lattice of the ion-ion interactions, we're thinking how strong are those charges? Is it +2? Is it +3? Is it -1? Is it -2? And how close can they get together? All right, what's the distance between them? And that comes down to how big is that atom really? All right, so if we were to rank them, right, I just want to recap all of the different types of interactions. This is what the AP curriculum really is looking at, the types of interactions. Ion-ion attraction, we're going to say, is the strongest. Ion dipole, that is going to be, now if we kind of disregard ion-ion, ion dipole is going to be the strongest attraction we can see. Now, dipole-dipole is going to be second. All right, so ion dipole, that's an ion with a polar molecule. Dipole-dipole, polar molecule with another polar molecule. Dipole-induced dipole, right? So that's a polar molecule with a non-polar molecule. And lastly, London dispersion forces. That is a non-polar molecule with another non-polar molecule. That's the fluctuations that we're looking at when we say London dispersion forces. But, and this is a big thing to keep in mind, the strongest net intermolecular forces tend to be our London dispersion forces when we look at larger molecules, right? The size will matter there. So the London dispersion forces often will be the strongest force, even though it's ranked last. it'll often be the strongest force because it's the strongest net force when we think about these large molecules. All right, so hydrogen bonding is something that we have seen. Hydrogen bonding, it's a very strong intermolecular attraction. Technically, hydrogen bonding is dipole-dipole, if we were to go back to our list. All right, but it only occurs when hydrogen is bonded to either a nitrogen, oxygen, or fluorine atom. All right, oftentimes textbooks will mention that these are the highly electronegative atoms. All right, sometimes we think, well, what about chlorine or bromine or iodine, the other halogens? The other piece that's really important for hydrogen bonding is the size. Now, nitrogen, oxygen, and fluorine, all being in period 2, they are relatively small. So we get this really big difference in size between the hydrogen and either the nitrogen, oxygen, or fluorine at that size. As we get bigger atoms, we don't get as dramatic of a difference because the hydrogen can't get that close to it. All right, so we have our NH3s, our H2Os, and our HFs. We've already seen the pattern they start to form. All right, so as a result, H2O ends up having the strongest hydrogen bonding because of the fact that it can branch out in 2 directions. Right, it's got a lot of surface area, and it's able to, because of its bent shape, form multiple attractions, whereas HF and NH3 typically only form 1 attraction at a time. The HF is a stronger attraction than the NH, right? So that's why HF will be higher than NH3. And we'll talk about this graph in a couple of slides. So don't worry about this graph, but just keep in mind, hydrogen bonding is something separate that only occurs with those 3 elements: nitrogen, oxygen, fluorine, and hydrogen bonding is the top of our intermolecular forces. It's a form of dipole-dipole. It's a special form, but again, only those 3 elements. Now, we have in large bimolecules, right? So like biomolecular, like these big bimolecules, we can get these non-covalent interactions that may start to occur between molecules of different regions or of the same large bimolecules. All right. All that's saying, it's just kind of just a fancy way of saying, if we think about important molecules from biology, our carbohydrates, our proteins, our lipids, our nucleic acids, obviously this is not a biology class, but there is chemistry going on in all of these. Obviously, again, this is not biochemistry, but it's a real simple thing happening with the intermolecular forces. All right. So proteins will fold, and we see all these crazy kind of pictures. They fold on themselves. That is a form of the protein. It's just a sequence of blocks. So in that folding, part of why it starts to fold is intermolecular forces between different regions of the same large molecule, right? So that folding is different parts of the molecule being attracted to other parts. So we'll see our hydrogen bonding in the NH, and we'll see some dipoles with the C double bond O. All right, so that's something like protein folding. It comes again in our DNA sequencing. All of our base pairs, right, they have those nitrogen backbones. We talk about the phosphate and the sugar. All of those base pairs, the TA or the CG, those are just hydrogen bonds between the 2 separate base pairs, right? And AT always has 2 attractions, that's the dashed line, and CG has 3. So the CG base pairs actually are a little stronger because they have 3 hydrogen bonding attractions versus the AT only with 2. So the reason I'm putting this in here, these could be prompts, right, where we have to look at a base pair. We're not doing a bio question. We're trying to look specifically for the intermolecular force there, so that dashed line. So boiling point. We began this video with talking about how intermolecular forces will explain all of these different physical properties. I'm only going to talk about boiling points in this video. There will be later videos with more depth on all those other physical properties, but boiling point. All right, so here we're looking at the boiling point of our halogens. And the boiling point, it's going to increase. All right, why is it increasing from helium to neon to argon to krypton to xenon to radon? The boiling point is increasing because there's more attraction with an element like radon or xenon, right? As we get, now boiling is essentially breaking apart the attractions between molecules in the liquid and getting them to be into that gas phase. Right? That gas phase is where we are with our social distancing, but that gas phase is where there's very little attraction. So we need to put in a lot of kinetic energy to get to essentially break apart those attractions. So our larger molecules have more electrons, they are more polarizable, they're going to have stronger London dispersion forces for the noble gases, and the boiling point is going to increase. All right, now that is for the noble gases. That would be the same trend if we were looking at diatomic molecules. Now, what about boiling points of molecules? All right, so here we have the carbon family. So CH4, then SiH4, then GeH4, and then SnH4. They're all going to have that tetrahedral shape. All right, carbon, silicon, germanium, and tin. As we go down the periodic table, right, the molecules, the atoms, these atoms get bigger, which means they have more electrons, and also their outer shell electrons are further away from the nucleus, so they become, again, more polarizable, right? More electrons further away from the nucleus, more polarizable, so we're seeing the boiling point trend increase again. All right, the SnH4 will have stronger London dispersion forces because of the more polarizable, more electrons than the CH4, higher boiling point. All right, same thing happens with our hydrocarbons, right? From methane through octane. So CH4, C2H6, C3H8, C4H10, C5H12, C6H14, C7H16, C8H18, right? As the number of carbons increases, that adds more electrons to the molecule, makes it more polarizable. It gives it stronger London dispersion forces because there's more fluctuations. All right, and as a result, it has a higher boiling point. All right, now here's an interesting slide. If we think about group 15 and group 16 and group 17, right? As we go down the group, their boiling points increase and they're all being bonded with hydrogen. So that makes sense. But where should the very beginning, where should the period 2 elements be? And again, when we think about the period 2 elements, we're thinking about oxygen, fluorine, and nitrogen. Well, when those bond with hydrogen, what do they form? That very special case, the hydrogen bonding. So as a result, when we have the hydrogen bonding leads to really high boiling points. All right. Now, again, we can only get the hydrogen bonding with those 3 particular elements: oxygen, fluorine, and nitrogen. Oxygen actually goes ahead of fluorine, even though fluorine has a higher electronegativity, because of the fact that the H2O is able to form those 2 attractions, whereas HF and NH3 are only able to form 1. And even though it's NH3, it's only forming 1 attraction because of the way that they almost block each other. So they lined up. We saw that image earlier. All right, now, if we have a comparable size, so we have methanol and ethane, CH4O, and ethane, C2H6, molar masses of 32 and 30. So now they're comparable sizes. If we look at their structure, the ethane, this is purely a non-polar molecule. Do not say it has hydrogen bonding. CH does not count as hydrogen bonding. But the methanol does. It's got the OH there. It has the hydrogen bonding, which is why its boiling point is considerably higher than the ethanes. So you can only use London dispersion forces to explain the difference between 2 molecules if the 2 molecules have the same size. Otherwise, if we're looking at size, it's almost always going to be the London dispersion forces unless we have that very unique hydrogen bonding occurring. All right, but no hydrogen bonding. It is purely going to come down to size. But when I say size, I'm specifically referring to the number of electrons, because more electrons means more polarizable. All right, so when it comes time to answer AP questions on intermolecular forces, and I know we have a lot more content in Unit 3 to discuss, but I just wanted to make a point with just the intermolecular forces themselves. Some of the do's. Do mention more polarizable. I've said it, I don't know how many times. Someone in the comments, please go back, watch it, tell me how many times I said more polarizable, but it is important. All right. Talk about more polarizable when you're talking about a bigger molecule with more electrons, because that's a correct way to answer these questions. Do mention hydrogen bonding only if it's got fluorine, oxygen, or nitrogen bonded to the hydrogen. All right. And do remember, London dispersion forces, while it is the weakest attraction, it ends up being the strongest net force as molecules get bigger. So even though we often think of LDF as being really weak, it ends up being our explanation for why a certain molecule has a stronger attraction, stronger force of attraction. Some of the don'ts. Don't mention mass as a reason for larger attraction. All right. Mention the more electrons. Don't mention mass. Don't say, well, this molecule has a bigger molar mass, so it's going to have more LDF. Right? Do not say that. Don't mention hydrogen bonding for CH. If you ever say, okay, well, it's got, if they show you a molecule with CH, you say, okay, it has hydrogen bonding, the reader will stop. You have already lost the points. It is over. So do not make that mistake. We will see a lot of structures with CH. Those are our organic compounds. They are not hydrogen bonding. They are not polar molecules, CH bonds. Don't say dipole-dipole is stronger than LDF to explain the difference between molecules of different sizes. All right, that's a very simple one. They might give you two molecules. They might ask you to predict which one's going to have the stronger intermolecular forces. One of them might be polar, the other one might be non-polar. You are going to be tempted to say, okay, well, the polar one has the dipole-dipole, so that's stronger than the non-polar one, which only has LDF. Well, did you compare the molecule sizes? All right, because the size will override that, right? As we get bigger molecules, more polarizable, we're going to get more net LDF attractions. All right, don't assume molecules are the same size unless it is stated. If the College Board really wants you to compare the intermolecular forces of comparable molecules, they will draw your attention to them being the same size. Right? They may have the molar mass listed in a chart with information, something like that. They will draw your attention to it. So you don't have to assume that. So don't assume that. And lastly, don't mention the term van der Waals forces, because the College Board, it doesn't like that term, right? Keep in mind, van der Waals forces should not be synonymous with LDF. Van der Waals forces, if anything, should be synonymous with any intermolecular force. All right, but again, it's just a term that we do not use. So this should be a good review of the intermolecular forces. In later videos, we will talk about more of the properties, how they change. We'll talk about the solids, liquids, and gases. We'll talk about the solutions, and we will talk about those electromagnetic spectrum pieces. So those will be coming in later videos. This is the beginning of reviewing Unit 3.